All right, our next concept in the unit of stoichiometry is a limiting reactant. If you will drop down and read the theory statement here, when there are two or more chemicals that are reacting and we know the amount of reactants that are present, the reaction will continue to consume reactants until one of them runs out. The limiting reactant is the chemical reactant, drop down here, that runs out and therefore it limits the amount of product produced. The amount of excess reactant will not fully get consumed, and therefore we do not want to do any calculations of the problems from it because it'll calculate an amount of product formation that is unattainable, mainly because of the fact that the limiting reactant will no longer be present, and therefore that product can't continue to form. So here, if we look at an example in real life where we're making cakes, one recipe for a cake calls for 3 cups of sugar, 4 cups of flour, 2 cups of milk, and 3 eggs. Well, if we have 16 cups of sugar in the refrigerator or in the pantry, okay, you can see there if I take 16 divided by 3, I can make 5 cakes and have a little bit left over. If I had 11 cups of flour, 11 divided by 4 can go into there 2 times. That'll get me up to 2 cakes. I'll have 3 cups left over, but I can't make a full cake if I only have 3 cups of flour. If I have 2 cups of milk and I have 14, that gives me 7 cakes. And 27 eggs gives me 9 cakes. So if each of these was a limiting reactant, these would be the most amount of cakes that I could make. So theoretically, how many cakes can I theoretically make based on how much ingredients I have at home? And the answer is 2. My limiting reactant is the flour because I can only make 2 cakes from it. I can't keep making cakes because I won't have any flour, which will give no body to the cake. I'll just have a bunch of soup. So with that, that's exactly the same process we're going to look at. We're going to have to figure out which reactant is going to run out first and therefore limit the reaction. And that is the one reagent we want to use for all calculations. Here's a conceptual application. We've already worked with this reaction before, the production of ammonia. And the perfect mixing ratio is 1 to 3. Well, if I were to mix 2 to 3, we'll see that 3 hydrogens will be fully consumed with just 1 nitrogen. We're going to have 1 nitrogen left. And because nitrogen remains when the reaction stops, we know that it is the excess reactant. Okay? Whatever reagent is left over when the reaction stops is the excess reagent. The hydrogen is the limiting reactant because it runs out and it also limits the amount of product production. And when we are done, we get a total of 2 ammonia molecules. So in my reaction vessel, I'll have 2 ammonia molecules and I'll have 1 nitrogen molecule left over for a total of 3 molecules will be present when the reaction stops. And that's something that my students always struggle with, is not figuring out how much product is produced, but by identifying how much excess reactant is left over. All right, so let's go ahead and do a problem now. If I turn the page, this shows an example of a problem from step to step of how to calculate the amount of product produced and also the amount of excess reactant left over. You can go through, stop the lecture now and read through that if you'd like, but I'm going to go ahead and do the next problem step by step so you can see that process and not just see the example worked out for you. But that's another option that you might want to do that you might find more useful than listening to me. I'll let you make that decision at home. All right? So, if 300 grams of iron oxide is mixed with 125 grams of carbon monoxide, how many grams of iron can be produced? Carbon dioxide is the other product. All right, so the first thing we need is the balanced equation. Fe2O3 reacts with the carbon monoxide to produce iron and carbon dioxide. All right, I'm going to pause the lecture now, balance that equation, and then start the lecture when you're done balancing it. All right, the coefficient should be 1, 3, 2, 3. All right, so now we have 300 grams of iron oxide. We have 125 grams of carbon monoxide. Now, what you cannot do as a student is just simply say, oh, this guy is smaller, therefore it must be the limiting reactant. That is incorrect because carbon monoxide has a much lower molar mass than iron oxide. Remember, the ratio that we get in the chemical equation, the 1 to 3, is not a mass ratio, it is a mole ratio. So the best way to do limiting reactant problems that I find, and still probably the fastest, is to simply just do two mass to mass problems back to back and figure out which reactant is going to produce the least amount of product. So we can see here the question is still asking how many grams of iron can be produced. So what we can do here is do a mass to mass problem where we take the 300 grams of iron oxide and we figure out how much iron could be produced from that amount if all of it were consumed. And then we do another problem where we take the grams of carbon monoxide and figure out how many grams it could produce in the same equation. Whichever reactant gives me the least amount is the answer to the problem. Okay, so that's one way of doing it, and probably the way that most of my students do it. Now there's other ways of doing the problem in which we could figure out how many moles each of these mass quantities are, and then apply the mole ratio to see which one will run out first, and then use that to figure out the product. The problem with that technique is usually by the time you do all of that analysis, while it's good science, you would probably be just as off faster just to do two mass to mass problems because you guys will be so good at them. And that's what I would expect most of you guys to do. So let's go ahead and do that. So we're going to start off with 300 grams of iron oxide, and we are going to go 2 grams of iron. A mass to mass problem, as we just took the quiz on, is a 3-step stoichiometry problem. All right, so whatever unit I start with, that unit goes on the top. The first step is to convert grams of iron oxide into moles. And we can do that by using the molar mass of iron oxide. The molar mass of iron oxide is the mass per 1 mole. Okay? Then that unit will be gone. Whatever unit is on top becomes the next unit on the bottom. The second step in a mass to mass problem is the mole ratio. This is where we get the balanced coefficients. In front of the iron, there's a 2. In front of the Fe2O3 is a 1. And lastly, we will convert the moles of iron into grams of iron by using the atomic weight of iron. And again, the molar mass of iron is the mass of 1 mole. All right, so whenever we do a mass to mass problem, we need to know the molar mass of the starting compound and the molar mass of the compound desired. And then the ratio is given by the coefficients. Okay, so now let's go ahead and add up. Iron has the molar mass of 55.85 times 2. There's 2 of them. Plus 3 oxygens is 3 times 16. So we get a molar mass of 159.70 grams. And iron has a mass of 55.85. Okay, so 300 divided by 159.7 times 2 times 55.85. We would produce 209.83 grams of iron. Okay? Now we have to do the same thing, but now with the carbon monoxide, figuring out how many grams of iron it could also produce. Okay, so we do the same exact process. 1 mole of carbon monoxide has the mass of 12 plus 16 is 28.01 grams. Is the molar mass of carbon monoxide. There's 3 moles of carbon monoxide. There's 3 in front of the coefficient. And there are 2 moles of iron, 2 to 3. And lastly, 1 mole of iron weighs 55.85 grams. All right, so we'll take 125 divided by the molar mass of carbon monoxide times 2 divided by 3 times 55.85. And we get 166.16 grams. So now we can see that 300 grams of iron oxide will produce 209 grams of iron. 125 grams of carbon monoxide will produce 166.16 grams. So in this problem, indeed, the smaller mass was the one that produced the least amount of iron, but that is something we can't just automatically assume. We have to show with good science and prove that the carbon monoxide is a limiting reactant, and these two mass-to-mass problems does that because the iron oxide produces more. So now the key thing is to identify your answer, and this is what you need to do on the test and the quizzes, is to say that 166.16 grams of iron will be produced. We can only produce the least amount of product that the reactant that produces the least amount of product will be the one that is the limiting reactant, and the reaction stops then. So the limiting reactant, if you were asked, is the carbon monoxide. Oops. The carbon monoxide is the reactant that will run out and will limit the amount of product production in this problem. Okay? So that's how you do a limiting reactant problem. You literally just do two problems going to the same product to see which one produces the least amount of substance. Okay? All right, so problem 3. If 90 grams of sodium is dropped into 80 grams of water, how many grams of hydrogen can be produced? So here is the reaction, which I would give you on the test. They didn't make no mention of the other product, so I would give you that. So here is the product. Here's the reaction. Now, let's go ahead. I'm going to pause lecture now. Go ahead and balance this reaction. When you restart it, I will have it balanced. So let's see if you can get it correct. So let's pause the lecture now and balance the reaction. All right, you should have 2, 2, 2, and 1 for the balanced reaction. All right, so now we have 90 grams of sodium, and we have 80 grams of water. We are asked to figure out how many grams of hydrogen can be produced. Okay, so now what you need to do is, just like I showed you in the previous problem, is do two mass-to-mass problems going to the same product of H2 so you can compare apples to apples and see which reactant will produce the least amount of hydrogen, and that'll be the answer. When you get to that point, restart the lecture, and we'll see if you did your mathematics right and you've identified the correct answer. And then I will lead you through step 4, step by step, which will be the last problem that I'll do today in today's lecture. Thank you. All right, the answer is 3.95 grams of hydrogen. So you can see my work up above, the 90 grams divided by the molar mass of sodium. The mole ratio is 1 hydrogen to 2 sodium, and the molar mass of hydrogen is 2.02. Doing the math correctly, we would get 3.95 grams of hydrogen. And the 80 grams of water, doing the same mathematical steps, the molar mass of water is 18.02. The mole ratio is 1 to 2, and the molar mass is 2.02 for a mass of 4.48. We cannot make 4.48 grams of hydrogen because once we make 3.95 grams, the sodium has run out, and therefore the sodium is the limiting reactant. 0 of the sodium would be remaining, and all of the sodium has been converted into products, and therefore the amount of product theoretically produced can only be the 3.95. So the amount of product produced is the smallest of the two values of the product that you're solving for. Okay? Lastly, this is probably the one place that students mess up the most, is being able to do the last step, which is figuring out how much excess reactant is left over. Remember, we have now determined that the excess reactant is the water, because it produces more product than the other reactant. So there will be some of this left. Now we've started with 80 grams. Okay, we want to figure out how much is left. So what we've got to do is we've got to figure out how much water has been used so that we can figure out how much is left. So how much of the 80 grams of water has been utilized? Now there's a number of different ways of doing this. Probably the simplest way is to take the two values from up above. We cannot attain 4.48 grams of hydrogen because once we get to 3.95 grams, we have fully consumed the sodium. So if I subtract the two values of the hydrogen and subtract them, we can figure out the amount of product that is not attainable because the limiting reactant has run out. So if I subtract these two, 0.53 grams of hydrogen would be the amount of hydrogen that could not be produced because the limiting reactant has run out. So now if I work backwards, I could now figure out how much water this would be. So if all of the water were to react, we would have none left. But since 0.53 grams is not able to be produced, we can work backwards to figure out how much water this would be, and that's how much water is, in essence, has been left, or is left over. Okay? So, 0.53 grams of hydrogen. This, again, is a mass-to-mass problem. The molar mass of hydrogen is 2.02. Okay, in the balanced equation above, the mole ratio is hydrogen to water. So we are literally doing the water reaction up here. We're actually literally doing it backwards now. So we end up getting 9.46 grams of water would be what's left over. And there's my answer. So this is one way of doing the problem. Okay, if this is a way that works for you, then I would say go for it. This is the way to go and do the problems. I'm going to show you a different way, and now you can choose which one you prefer. In this way, we pick the limiting reactant, and we do a mass-to-mass problem to figure out, okay, I know the sodium is going to run out. How many grams of water would it take to fully consume the sodium? All right, so now the molar mass of sodium is 22.99 grams of sodium. Convert that to moles. We're going to do the mole ratio of sodium to water, which is always the second step in the problem. The coefficients is 2 to 2 from our balanced equation way up above. And again, the molar mass of water is 18.02. So if I take 90 grams of sodium, the limiting reactant, I know it's going to run out. When that guy runs out, how much water has it consumed? 70.54. So this is the amount of water that it has used up in the problem. Well, we started with 80, so this is gearing at this conceptual application I just talked above. So if I take 80 grams minus 70.54 grams, we get 9.46 grams of water, which would be left. So you can see both ways give me the same exact answer. Pick the way that you think would be or make the most sense to you. Okay? In the first way, I subtracted the amount of products to figure out the amount of product that is unattainable, and then work backwards to figure out how much excess reactant that must be left over. Or take the limiting reactant and figure out how much of the excess reactant it consumes, and then subtract to get the final answer. In both cases, you'll notice that you do a subtraction followed by a mass-to-mass problem. It just depends on what order you want to do it. Okay, so here are two different ways of doing it. Pick the way that makes sense to you the best, and that is how you can do or calculate the amount of excess reagent that is left over. All right, so your homework next page 13, you can just skip over this one. Have this page 13 done too if you want extra additional practice. You could do this problem as well and have extra practice. So all pages, page 13. I would like you to go ahead and do part B, questions 1 through 6. And I apologize, question 5 popped on towards the bottom. I'd like you to go ahead and do problem B and go through all these problems as good practice in limiting reactant problems. Okay? If you have any questions, reach out to me, but again, I'll have the answer key supplied online. I'll also, 14, you could probably just finish it off on the bottom here of this problem if you want. But and 15 will be on Canvas. Again, pick and choose the amount of problems you need to do to get really good and proficient at them, and I'll let that be your choice. Okay? Again, thanks for listening, and we have one more lecture to do in this unit, which is on percent yield.